Let's take a look at an application of linear inequality in two variables. So we have the following scenario. A company produces widgets that consist of two types of metals. One metal costs $4 per pound, and the other type of metal costs $2.50 per pound. In order for the company to make a profit, it needs to produce the widgets at a cost of no more than $10 per pound. We want to find all the possible combinations of weights of the two types of metals. So let's go ahead and begin by defining a few variables. So we have x and y. We're going to let x equal the weight of the first metal. Remember, we want all the combination of the weights of the two types of metal. So x is going to equal the weight of the first type of metal. And we're going to let y equal the weight of the second type of metal. All right, so this is just fairly straightforward. We're just defining both of our variables in terms of what we're being asked to find. And these are both going to be in pounds. All right, we're going to scale them in pounds, and we want to find all the possible combinations of the weights of the two types of metals to where this company can produce these widgets and make a profit. So the next thing we need to do is we need to identify our pertinent information and put it together to write the inequality. So let's see what the keywords that we have. Well, we have our first metal is $4 a pound. Our second metal is $2.50 per pound. And we know that the company needs to produce the widgets at a cost of no more than $10 per pound. No more than $10 per pound is the reason why this is a linear inequality, because we're looking for an interval of values instead of just one value. All right, so let's go ahead and use these pieces of information to write a linear inequality in terms of our variables. So we have our first metal is $4 per pound, and x is the weight of the first variable. So the cost of the first metal is 4x, $4 per pound times the number of pounds, and the cost is going to be that plus the weight of the second metal times the cost per pound of the metal. So 250 or 2.5 y. All right, now this total weight needs to be no more than $10 per pound. So the cost of this total weight can be no more than $10 per pound. It can be $10 per pound, but it can't exceed $10 a pound. So that means we want all the values that are less than or equal to $10. All right, this is the most important part, going from a word problem and constructing some sort of linear inequality that describes this word problem accurately. So make sure you understand how we got this, because we can actually deal with this pretty simply now that we have a linear inequality. We know how to do this. All right, so now that we have an inequality to work with, the hard part's over, so we simply need to solve and graph. So let's go ahead and use what we know in the previous section. Let's go ahead and convert this from standard form into slope-intercept form so we can get a graph of what it looks like. So let's go ahead and solve for y. So we're going to subtract 4x from both sides. And I apologize, this is 4x, not 9x. These two terms cancel, so we have 2.5y is less than or equal to minus 4x plus 10. And we can go ahead and isolate our variable by dividing everything through by 2.5. Actually, let's go ahead and convert this. I like dealing with fractions instead of decimals. So over to the side, 2.5 is the same thing as 2.5. And to put it in improper fraction, we have 2 times 2 is 4, plus 1 is 5. So we can convert this to 5 halves. So while we're dividing 2.5 right here, we're going to divide by 5 over 2 over here. We're just dividing all three terms by the same term. So we have y is less than or equal to, let's convert minus 4 into minus 8 over 2. Excuse me, that's a weird looking 8. 8 over 2. And we can convert plus 10 into, well, we can just say it's 20 over 2. So 10 is the same thing as 20 over 2. So let's go ahead and write this as minus 8 over 2 divided by 5 over 2. Make our next step more easy. So we have 20 over 2, same thing as 10, divided by 5 over 2. Let's go ahead and write out the next step. So we have y is less than or equal to. When we're dividing by a fraction, we don't ask why, but we flip the second and multiply. So minus 8 over 2 times the reciprocal of 5 over 2, which is 2 over 5. We're multiplying these together, and we have plus. We're going to do the same thing with the second set of fractions. We have 20 over 2 times the reciprocal, which is 2 over 5. And you can see we can simplify things to make our calculations much simpler. These two will just pull out a factor of 2. Same thing here. These will become 1s. We can factor out a 5 out of these two terms, making this a 4. Now this is going to be much nicer to deal with. So we have minus 8 times 1, which is a minus 8 over 1 times 5 is 5. And we forgot our x term here. Remember, we have our x term and our x term. So I have minus 8 over 5x plus 4 times 1 is 4 divided by 1. So it's just 4. We can just write this as 4. There we go. Okay, so we have our linear inequality in slope-intercept form. All the hard part's over, so we can just simply pick out a few easy points, or a few easy values to find the 3 points. So we have x, let's let x equal 0. That gives us y is less than or equal to, or excuse me, y equals, we're looking for 3 points. Y equals 8 over 5 times 0 plus 4. Those two terms cancel, so we have y equals 4, which means we have our first point of 0, 4. Let's find another one. We have x equals 1. So when x equals 1, y equals minus 8 over 5 times 1 plus 4, which gives us minus 8 over 5. Let's go ahead and convert 4 to a fraction with the denominator of 5, which is 20 over 5. That'll give us a positive 12 over 5. So our second point is 1 and 12/5. Let's squeeze in our third one down here. We have x is equal to a minus 1. When x equals minus 1, y is equal to minus 8 over 5 times minus 1. These two negatives will cancel. We have our plus 4. So we have 8 over 5 plus 4, which we saw up here is the same thing as 20 over 5. So we have 8 plus 20 is 28 over 5. And this is our third point. Minus 1 and 28 over 5. So we have our 3 points that we can graph now. We're going to go ahead and clear all this so we can have some room. So everything but our 3 points. Okay, so let's go ahead and graph this thing. So here's our y-axis. Here's our x-axis. That's our y-axis and our x-axis. All right, our biggest term is 5, or a little over 5. 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so here we go. Let's go ahead and plot these. So we have 0, 4, which occurs right here. We have 1 and 12 over 5. 12 over 5 is the same thing as 2 and 2/5. So that's about right here. And we have the point minus 1 and 28 over 5. 28 over 5 is the same thing as 5 and 3/5. 1, 2, 3, 4, 5. So we have about right here. Okay, and I apologize. This is not to scale. Didn't scale it very well. But regardless, we're looking for no more than $10 per pound. Now, if you recall that we erased our original equation, our original inequality in slope-intercept form was y is less than or equal to minus 8 over 5 x plus 4. All right, this is our original linear inequality in slope-intercept form. So we want a solid line. We're going to include all the values on the line. So we're going to have a solid line here. Well, let me draw it a little straighter than that. We're having a solid line here that goes in both directions. Now, it only theoretically goes to the negative side. We actually can't have a negative weight or a negative cost, so this side's just theoretical, as is this side down here. So what we can do here is we can shave off both negative sides and just stay in quadrant 1. We know that it goes in both directions infinitely, but we're only interested, because this is actually a real-world application, we're dealing with a specific quantity. We're only dealing with quadrant 1. Alright, so we can actually just stay in quadrant 1. It doesn't make sense to have a negative weight or a negative cost. Now we plotted the point -1 and 28/5 just to make sure we drew an accurate line, but we only include the shaded region that we're about to shade. So we're looking for all the values that are less than or equal to this particular expression. So we want all the values underneath the line, but we want to stay in quadrant 1. So all of our values to satisfy this equation is right here. Okay, we just want all these values right here. Everything in between the two axes and this line. Now this region gives us all the possible combinations of weights of the two types of metals that will keep production costs less than or equal to $10 a pound. Alright, so this actually is something that would come up maybe in a business report or a presentation for a particular manufacturer. So this is an application of a linear inequality and two variables, and when you get into industry and actually use this in the real world, this is actually very useful. Now, we usually don't do it by hand. We have computers doing it these days, but this is actually the math behind what's going on when we're talking about making a profit. So look over this example a few times just to get really familiar with it, and it's actually really fun to see the actual real-world applications when talking about saving money. So very important. I'll see you in the next video.